All right, so now is the next part of this, and I think this is where I thought things get kind of interesting. And this is where we'll find out why people out of Lawrence Livermore National Labs, which is focused on nuclear fusion of all things, wanted to do this. So, why would we want to use a reinforcement learning approach besides some of the things I was talking about for this problem? And the reason is you want to create policies around control, active control. And so this is the National Ignition Facility in California. This is, I think this is an artist rendition, but I'll show you what it really looks like in a second. This is for creating fusion reactions. This is a multi-billion-dollar facility in the United States for doing this. And the main idea is you start a fusion reaction and you use lasers to control it. So you can, get it to the point where it could be, you can actually harness energy out of it. The lasers, change their settings dynamically based on what's going on in the fusion reaction. So you have this multi-dimensional reaction to the fusion reaction. They didn't say it in the paper, but to me, I think this is why they are spending so much time on this problem. I mean, that's like the main thing that's out there. And this is what it looks like. I actually visited there a long time ago. It's like the Death Star inside there. It really is. It's crazy. So here's an example of one of the problems they looked at. So what we've got here, and I think I can build this slide. Yeah. So we got a continuous state space, and we got these variables S1 through S8. So a state is just a value assigned to S1 to S8. That's one state. And based on those values, in this case, this little lunar lander is going to take some action that in here consists of two scalar values, A1 and A2. So one is like, I think, a thrust and a yaw or something like this. And so in order to make the lunar lander do the right thing, it's responding to its environment, which is those S1 through S8, and A1 and A2 is this reaction to that, and those are the formulas there. So why symbolic policies for control? Well, traditional control theory from mathematical physics gives you these really simple models, kind of like what we saw in the last slide, and those are great. Deep reinforcement learning doesn't give you anything like that. It just gives you a black box, which can be very effective, but there's no way to take a look inside and see what it's doing. And so the whole idea here is, can we sort of have the best of both worlds? Can we have the data-driven aspects of deep learning, but still have the mathematical expressions from control theory? And of course, deep RL is designed to, or deep symbolic regression is designed to be the solution to this. So why not use symbolic regression directly? Well, the authors cite what they call an objective function mismatch, because the reason is if you use symbolic regression directly for each of those action dimensions, because notice the lunar lander had two, you're going to have this objective function mismatch where each action function is being optimized towards something different, and it's not being optimized toward the ultimate goal of the agent. And they showed in their experiments this just gets you catastrophic failure. So we have, here's the reward function. And again, we have number of episodes, time steps, reward for time, and so on. Pretty standard. All right, so the key thing they had to add was considering these multiple dimensions. Now, going in a straightforward way and learning a mathematical expression for each dimension leads to a combinatorial blowout. So that's no good. And what they came up with, I think, was pretty interesting. And if anyone looked at that paper Chita Baral talked about at the end of his talk, that's using abductive inference for as part of the learning process. They actually use a similar technique, and that is they'll have a black box neural model that they call an anchor, and they use it as placeholders for the values they haven't learned yet. And so what they do is they say, so if I have, let's say, 5 actions I'm trying to learn, and I'm already at an iteration where I've learned actions 1 and 2 symbolically, actions 4 and 5, I'll use stuff from the anchor model, the black box neural model, and I'll only learn action 3. And it turns out this works pretty well. So here's the overall approach. But notice, like, I mean, this thing I highlighted here with the box, this is pretty much the exact same thing from the earlier paper. And so here, when we get into multiple dimensions, this is where you see in the red box on the screen, you notice you have F bar from 1 to I minus 1. These are the previous iterations. So these are the functions that have already been learned using symbolic regression. F of S is the new thing. And then psi I plus 1 through N, this is coming from the anchor model. So some additional optimizations are also introduced. Again, they have this entropy regularization thing that they throw in there as well. They also come up with this thing, what they call a soft length prior for the episode length. And the reason why they use this is they found that when they just specified something as a maximum, everything would use as much as it could. And so this kind of led to a little bit of variety there, if you will. So they examine this. So here the DSP, and the DSP with the footnote is without the constant optimization. But they explored this on the, kind of open AI gym suite of various reinforcement problems. And here are some of the equations that resulted from it. I think they're, they kind of are interesting looking, but they're still pretty simple, right? Also note that you have multiple dimensions here. Even going to the bipedal walker, you got 4 different action dimensions going on. Now, how does this perform? Actually turns out to perform quite well, even against other deep reinforcement learning approaches. The column in this table labeled regression is using symbolic regression in sort of the naive way. And this is where you get the catastrophic failure. It's last in almost every experiment, and sometimes even producing negative reward. But again, what's kind of neat about this is the performance is really quite good, but it's giving you a symbolic result, which I think is neat.